In this video, we are going to talk about hypothesis testing and using SPSS in data analysis with Pearson correlation coefficient, or Pearson's R, as the statistical tool. To start with, what is Pearson's R? Pearson's R is a parametric statistical tool that measures the correlation or relationship between two variables. It gives us information about one, the magnitude or strength of the correlation, whether small, medium, or large, as well as the direction of the relationship or correlation, whether positively correlated or negatively correlated. The coefficient values range from -1 to 1, where 1 indicates a positive relationship and -1 indicates a negative relationship, while 0 indicates no relationship at all. Just like any tools, Pearson's R have its limitations. In terms of variables, both variables should be continuous, or what we call the scale variable, whether interval or ratio. This is because this type of data possesses the properties of magnitude and equal intervals between adjacent units. An example of a scale variable is age. An increase in age from 21 to 22 would be the same as an increase in age from 60 to 61. This is what we call equal interval. Now, if one or both of the variables, however, are ordinal in measurement, for example, educational attainment, then the Spearman correlation, a non-parametric tool, which is the counterpart of Pearson's R, could be conducted instead. Next, in terms of sample size, a minimum of 2 variables, as mentioned earlier, with at least 3 observations for each variable are needed in order for the test to be meaningful. We may use 8 to 10 paired observations, although a larger data set may be needed if the data sets are skewed. So this only shows that the larger the sample size, the better it is in order to detect patterns in the data. Lastly, in terms of assumptions, we can only use Pearson's R if all of these assumptions are met. For example, both variables should be normally distributed. So if plotted in a graph, normally distributed variables have a bell-shaped curve. Next, both variables should be linearly related to each other. Using a scatter plot that can be generated in SPSS, the values of the variables should yield a relatively straight line as shown in this example graph. Okay, or we can also plot it like that. All right. So next is both variables should be homoscedastic. That means that the data is equally distributed about the regression line. For example, if we pick this data and this data, both data have actually almost the same distance from this line. So both variables should be homoscedastic. Next, let's start testing our hypothesis using SPSS. Our research question is there a significant relationship between post-test and grade scores? There are 5 steps to test this hypothesis. Step 1, first, we have to state the hypothesis. So there are 2 types, the null hypothesis or HO and the alternative hypothesis or HA. So our HO or null hypothesis is there is no significant relationship between post-test and grade scores. There's no difference. While our alternative hypothesis is there is a significant relationship between post-test and grade scores. Step 2. So in step 2, we state the level of significance. At this point, we set our alpha to be 0.05 or 5%. Step 3, we choose our statistical tool and we use Pearson's R, assuming that all assumptions are met. In step 4, we collect the data and perform the analysis. So to test if the post-test and the grade scores are related, post-test and grade scores were collected from 30 individuals, being our sample size, and using alpha value of 0.05, we will test our hypothesis if post-test and grade scores are actually related. To do this, we open our SPSS software. We go to Analyze, click on Correlate, and Bivariate. This leads us to this table, the bivariate correlations. And in here, we select our 2 variables, the post-test and the grade score, and we move them to this variable box. And then we tick Pearson, being our statistical tool. We select two-tailed, and we click OK. Click OK. This will generate us the output table, our correlation table that shows this data. Now in this table, it shows the relationship of post-test and post-test to be, of course, 1, being the highest or the perfectly positive correlation. As post-test increases, of course, post-test also increases. And then the relationship of post-test with grade score at 0.450, which is statistically significant. Sig value is our p-value, which is 0.012, and n is our sample size, which is 30. Now, on the second row, we see that the relationship of grade score with post-test and the relationship of grade score with grade score. So basically, these are identical data. They are the same, but only in opposite of each other. Okay, now if you can see here, this is actually the result of the correlation test. And it says here that the correlation is significant at 0.05 level. That is because if we plot it here, we will see that our p-value is 0.12, which is less than 0.05. And as a rule, when the p-value is greater than our alpha of 0.05, we do not reject HO. But if our p-value is less than our alpha value of 0.05, we reject HO. So what does it mean when we reject HO? When we reject HO, we conclude that there is a significant relationship between post-test and grit scores. In terms of magnitude or strength of correlation, the post-test and grit scores are actually not in terms of, okay, let's talk about this one. In terms of strength or magnitude, the post-test and grit scores have medium association at 0.450 value based on Cohen standard, being 0.10 and 0.29 to be small association, 0.30 and 0.49 to have medium association, and 0.50 and above to represent a large association or relationship. And let's just go back to this point. In terms of direction of association, the post-test and grit scores are of course positively correlated at 0.450 value. Thank you for watching. I hope you learned something today.